Welcome to This Explainer. Today, we're going to investigate one of the absolute most bizarre, massive physical phenomena happening right now, deep inside our solar system's largest planet. You know, when we look at Jupiter, we're usually totally captivated by its beautiful, swirling clouds, its massive storms, and those iconic alternating light and dark belts. But beneath that visible upper atmosphere, way down in the crushing, pitch-black depths of the planet, there is an alien weather system at work. And it's a weather system that completely redefines our understanding of planetary physics. By the end of our time together today, you're going to see exactly how this hidden mechanism shapes the very evolution of the gas giant.
Okay, let's dive into this. The whole phenomenon actually starts with a massive cosmic discrepancy. You see, Jupiter was the very first of the Sun's planets to form. Because of this, it's mostly made of the exact same primordial stuff as our Sun. We're talking specifically molecular hydrogen and helium. But here's the catch. When the Galileo entry probe plunged into Jupiter's atmosphere back in 1995, it sent back some highly unexpected data. The probe measured Jupiter's helium mass fraction in the upper atmosphere at 0.23. Now, that might just sound like an arbitrary number, but here is why it matters so much. That is significantly lower than the primordial solar abundance of 0.274. So, in simpler terms, compared to the Sun, Jupiter's upper atmosphere is missing a massive chunk of its helium.
So, we have a missing persons case on a literal planetary scale. Where did all the missing helium go? I mean, it didn't just evaporate into space. Jupiter's gravity is way too strong for that. The answer has to lie deep inside the planet. And to solve this mystery, we have to descend far past the visible troposphere, way past the water clouds and the lightning strikes, and journey deep into the Jovian interior, where the laws of chemistry and physics just behave in ways that are entirely alien to us here on Earth.
Now, to understand where the helium is hiding, we first have to understand the extreme environment down there. As we travel down into Jupiter, the pressure and temperature absolutely skyrocket to unimaginable levels. At depths of more than 10,000 kilometers below the cloud tops, the pressure becomes just completely crushing. We are talking millions of times our atmospheric pressure on Earth. Under these extreme conditions, hydrogen undergoes a radical transformation. It literally stops being a gas. It stops being a normal liquid too. The molecules are squeezed so tightly together that the electrons just detach from their atoms and start flowing freely. The molecular hydrogen transforms into a completely bizarre state known as liquid metallic hydrogen.
Now, what's really interesting about this slide is how we actually visualize this, because we obviously can't send a camera 10,000 kilometers deep into Jupiter. So scientists rely on advanced supercomputer simulations, specifically density functional theory molecular dynamics models, to picture this invisible world. These models map out the density of valence electrons in this incredibly high-pressure soup of hydrogen, helium, and heavier elements, and they reveal something fascinating about this metallic hydrogen environment. Up in the clouds, hydrogen and helium mix perfectly fine as gases, right? But down here, under this intense pressure, they suddenly stop getting along. The metallic hydrogen essentially rejects the helium.
And this rejection is exactly what triggers the mechanics of our alien weather system. The whole process relies on a concept called immiscibility. Just think of a bottle of oil and water. You can shake it up all you want, but eventually those two liquids are going to separate because they are immiscible. They literally just can't mix. Deep inside Jupiter, the exact same thing is happening. As the molecular hydrogen transitions into metallic hydrogen, the helium becomes completely immiscible. It separates from the metallic fluid. But because the environment is so dense and highly pressurized, the helium doesn't just form bubbles that float to the top. Instead, it forms incredibly dense droplets.
Picture this. At the exact moment of separation, the helium literally condenses out of the surrounding metallic fluid, clumping together to form these distinct droplets. It is exactly like water vapor condensing into rain droplets in our own clouds here on Earth, except it's happening with liquid metals and noble gases under pressures that would crush a submarine like a tin can. This extreme phase transition marks the birth of a terrifying internal storm, unlike absolutely anything we could ever experience on the surface. Because these newly formed condensed helium droplets are physically denser and heavier than the surrounding liquid, gravity just takes over. Vast, continent-sized regions deep inside the planet become totally engulfed in a massive storm where it is literally raining liquid helium downward, straight toward Jupiter's rocky core. The calculations suggest that this rain separates from the hydrogen around 11,000 kilometers below the clouds and merges again much, much deeper down. And guess what? This immense continuous internal rainstorm is precisely the mechanism that depletes the upper atmosphere of its helium. Now,
If you're a skeptical learner, you might be thinking, okay, that's a really great theory, but how do we prove it if we can't physically see it? Well, the proof is actually in another missing element: neon. When that Galileo probe measured the atmosphere, it didn't just find a lack of helium, it found a severe depletion of neon as well. And that, right there, is our smoking gun. You see, neon is an element that very easily dissolves into liquid helium. So, as the helium rain droplets form and fall toward the core, they're acting like a giant planetary sponge, just soaking up the neon and dragging it all down with them. The missing neon perfectly, beautifully confirms the existence of the helium rain.
So the crucial point is that this helium rain isn't just some fun piece of trivia. It fundamentally alters the structure and the evolution of the entire planet. This rain creates a really distinct layer of immiscibility, which is essentially a boundary between the outer molecular envelope and the inner metallic core. And this layer acts as a massive convective barrier. By inhibiting effective convection, the deep interior of Jupiter stays much, much hotter than it normally would, significantly delaying the cooling of the planet. It's essentially acting as a huge thermal blanket, wrapping around the core and stabilizing the structural differences between Jupiter's internal layers over billions of years.
And we can see this effect when scientists chart the data. By taking temperature and pressure data, like the profiles tracked by the Galileo probe, and comparing it to theoretical models of helium and hydrogen mixtures, researchers can pinpoint exactly where this convective barrier exists. The temperature profile tells us that because of this helium rain, Jupiter's internal heat isn't just escaping evenly out into space, it's trapped and compartmentalized. And that entirely rewrites our understanding of the planet's cooling age. Let's move to and see how this builds today, because this investigation isn't just history, it's happening right now. Since 2016, the Juno spacecraft has been orbiting Jupiter, conducting an incredibly deep dive into these very layers. Since we still can't see the rain directly, Juno measures it using gravity. Jupiter's rapid rotation and internal mass distribution create anomalies in its external gravitational potential, what scientists refer to as zonal harmonic coefficients. By tracking exactly how the spacecraft is pulled by these gravity waves, and by using microwave radiometry to look deep past the ammonia and water clouds, Juno is actively mapping the boundaries of this helium rain layer with unprecedented precision.
The discovery of this helium rain fundamentally shifts how we view gas giants. They aren't just uniform, boring balls of gas. They are incredibly complex, layered engines driven by completely alien weather. And this leaves us with a totally thrilling question. What other bizarre physical phenomena are hiding in the unmapped depths of gas giants? I mean, if Jupiter has continent-sized helium rainstorms, just consider this. Scientists already suspect that deep inside Saturn, Uranus, and Neptune, the crushing pressures actually cause carbon atoms to crystallize, resulting in literal rainfalls of solid diamonds. As we continue to map the gravity and interior structures of these massive worlds, you really have to wonder, what other incredible mysteries are waiting to be uncovered in the dark? Thanks for exploring this explainer with me, and definitely keep questioning the universe around you.